Okay, so now we can evaluate Taylor or expand Taylor and Maclaurin series a- by manipulating them. So, like applying operations to them. So the different operations that we can use are we've already seen like substituting um, an x value or an input into a series. We can now multiply or divide a series by another series or by a constant or a variable. We can add or subtract two series together, and you can differentiate or integrate a series, which we've seen integrating a series. All right, so let's go ahead and we are going to find the first four non-zero terms of the Maclaurin series. F of x is equal to sine x is equal times cosine x. So Maclaurin series means that we are centering around c is equal to 0. That's our starting value. I know that sine x is equal to x minus x cubed over 3 factorial plus x squared over 5 factorial minus x to the 7th over 7 factorial. Okay, and I'm going to be multiplying these two series together, so I am going to make an area model. I'm going to try at least. Ooh. Okay, so this guy is equal to sine x, and then cosine x is equal to 1 minus x squared over 2 factorial, or just 2, and then x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Okay, we're going to multiply these together, and I get, let's see, 1 times x, okay, x, negative x cubed over 3 factorial, x to the 5th over 5 factorial, negative x to the 7th over 7 factorial. Okay, and then negative x to the 3rd over 2 x to the, we're raising the, I'm going to go downward actually, and then do x to the 5th over 4 factorial, and then x to the negative x to the 7th over 6 factorial. Okay, so in the middle, x squared times x cubed, x to the 5th, a negative times a negative is a positive, and then 2 factorial times 3 factorial. And then we have here, we're going to end up with a negative 7x over 3 factorial times 4 factorial, and then x to the 9th, positive x to the 9th times 3 factorial times 6 factorial. Okay, so x to the 5th times x squared is negative x to the 7th over 5 factorial times 2 factorial, then x to the 9th over 4 factorial times 5 factorial. And then I'm going to go ahead and just skip this one because that's x to the 11th. So I'll multiply it if I need it, but I'm only looking at the first four non-zero terms of the series. So I don't think I'm going to need that x to the 11th. Okay, so I'm going to do x to the 7th times x squared gives me x to the 9th over 2 factorial times 7 factorial. Okay, so what we're doing is we're saying f of x is equal to the sine of x times the cosine of x, which really we know we can expand these to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus minus x to the 7th over 7 factorial times the cosine of x expanded in its, oh wait, we should put plus dot 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 because that keeps it an exact value. So 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Oops, plus dot dot dot. Saying it goes on forever, okay? So the thing about multiplying polynomials is that, remember, you had to like we're like super gonna distribute. So I use the area model to multiply, and I get f of x is equal to the x to the first power, and then I'm going to add the x cubed term. So it's going to be minus, and I did this in the calculator, 2x cubed over 3 plus, let's go ahead and add our x to the 5th terms here. That gives me 2x to the 5th over 15. And then finally, my last non-zero term is going to be these x to the 7th. When I add those 4 terms together, I get negative 4x to the 7 over 315. So we would, if I put plus dot dot dot, this means that the series is going to go on forever. So this is the exact value of sine x times cosine x if I expanded this series out to infinite number of terms. Now, if I wrote the polynomial of x, if I wrote only the first 4 terms, so if I said sine x times cosine x is equal to x minus 2x cubed over 3 plus 2x to the 5th over 15 minus 4x to the 7 over 315, and didn't write the dot 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 saying this goes on forever. This is an approximation, so I would need to change my equal signs to an approximation. Okay, so the polynomial is an approximation. The series that goes on to infinity is the actual value of your function. Okay, so we're going to find the Maclaurin series. So again, that means when we're centered around 0. And so when we say find the Maclaurin series, we want to find the general term. And then also we're going to find the first 4 non-zero terms of f of x. Okay, so I have, so I can rewrite this as sine x times sine x. Remember when I have a polynomial times another polynomial, I actually have to expand by area model or by multiplying out each term, and that's a pain in the tuchus. So I am going to use my trig identities, which is amazingly less of a pain. Okay, so what I know is that sine squared x is equal to 1 minus the cosine of 2x. That way I don't have to square that trig identity, that trig function, all over 2. Okay, so I can see I'm going to use the cosine of x expanded, which is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8 over 8 factorial plus dot dot dot. Okay, if I want to do the cosine of 2x, just replace all the x's with 2x. So 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus 2x to the 8th over 8 factorial. Okay, so now I can go ahead and write this as 1 minus the cosine of 2x all over 2. And I'm just going to copy it and paste it. Okay, so I have, let's add our plus dot dot dot. Okay, so that's the cosine of 2x. I'm going to put a 1 in front and subtract the cosine of 2x and then divide by 2. Okay, so when I divide by, what I notice is that all of my signs are going to change and my 1s are going to cancel. So I'm going to make that a plus, and that's going to be a plus, a minus, a plus, a minus, and a plus. Okay, and then the 2 I'm going to multiply by 1 over 2. So every factor in the denominator, every term's denominator will have a factor of 2 in it. So I'm going to have 1 minus the cosine of 2x over 2 is equal to 2 2 squared times x squared. I'm going to go ahead and write it like that. 2 squared over x squared over 2 times 2 factorial minus 2 squared, 2 to the 4th times x to the 4th over 2 times 4 factorial plus 2 to the 6th over x to the 6th times 2 times 6 factorial minus 2 to the 8 times x to the 8 over 2 times 8 factorial plus dot, dot, dot. Okay, I can divide a 2 into the numerator here, into each one of these, so it decreases the power. So the 1 minus the cosine of 2x over 2 is equal to 2x squared, or 2 to the 1 x squared over 2 factorial, minus 2 cubed times x cubed over 4 factorial, plus 2 to the 5th times x to the 6th over 6 factorial, minus 2 to the 7th over x times x to the 8th over 8 factorial, plus dot, dot, dot. Okay, and so I can see that the general term, if I make this n is equal to 0, n is equal to 1, n is equal to the 2 term, and n is equal to 3, then what I'm going to end up with is the negative. So -1, because the signs change. And all the odd terms right now are negative. So I'm going to keep this regular n, because odd terms will make our odd powers will make our signs negative. And then we have each one of these 2's here, and those 2's look like they're off by 2n plus 1. So I'm going to double the n. So 1 times 2, let's see, 1 times 2 plus 1 will give me 3. 1 times 2, 2 times 2 plus 1 will give me 5. 3 times 2 plus 1 will give me 7. And I can see I have a mistake right here. This should be x to the 4th. Okay, so this is 2 to the 2n plus 1. And then the power of x is x to the 2 times n plus 1. Okay. All over. And the power in the denominator also matches. So we get 2 times n plus 1. Oops. Times n plus 1. All of that factorial. Okay. All right, let's go on to the next one. So we have our general term and our series expanded to the first 4 non-zero terms. All right, we're going to find a Maclaurin series centered at C. And the first non-zero term, 4 non-zero terms of e to the 2x. Okay, so I'm just going to start with e to the x. And I know that is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus, and then the general term would be x to the n over n factorial. Okay, so I can write e to the 2x as really we're just replacing x with 2x, so 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus, okay, our general term would then be, instead of x, we've replaced that with 2x to the n power over n factorial. If I wanted to write this as a summation, this would be the sum from n is equal to 0, because this 1 represents my 0 term, my first term. You can write the rules starting with n is equal to 1 or n is equal to 2, but they're obviously going to be a little bit different depending on what n value you start with, and you define that by putting that in your summation notation. Okay, so I started with 0, and we're going to go to infinity to make this a series. Okay, and what I end up with is the sum of 2x to the n over n factorial. Or suppose you could write it as 2 to the n times x to the n over n factorial. Okay. All right, let's do a couple more. Find a Maclaurin series in the first 4 non-zero terms of f of x is equal to e to the x plus e to the x, e to the negative x over 2. All right, so I'm going to start with e to the x. I'm just going to write it out, and then and then I will go ahead and add them together, because you can add series together. Okay. Just like you can add a function together. Really, remember the series is just a polynomial representation of the function. I think I forgot a 5. 5 factorial plus x to the 6 over 6 factorial plus ... because remember it goes on forever. Okay, and then what I'm adding to that is e to the negative x. So I'm actually going to just write it underneath. So I have 1 minus x plus, and then x squared over 2 factorial. Then this is going to be negative x cubed. So it's going to give me negative x cubed over 3 factorial plus positive x to the 4th over 4 factorial minus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus ... So adding these up now. So e to the x plus e to the negative x. 1 plus 1 is e to the x plus e to the negative x is equal to 1 plus 1 is 2. These cancel. Then I get 2 plus 2x squared over 2 factorial cancels, plus 2x to the 4th over 4 factorial cancels, plus 2x to the 6th over 6 factorial. Okay, and then the last thing we would need to do is divide all this by 2. So I have e to the x plus e to the negative x over 2 is equal to 2 plus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial plus 2x to the 6th over 6 factorial all over 2. All right, multiply by the reciprocal. So that gives me a factor of 1/2 in each one of these terms. So I'm just multiplying it in. Okay, so I'm going to end up with e to the x plus e to the negative x all over 2 is equal to 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial. And it said the first 4 non-zero terms. So there's the first 4 non-zero terms plus ... And then I am going to write this, the general series. So as n is equal to 0 to infinity. So if I make 1 is the 0 term, the first term is x squared over 2 factorial, second term, third term. The pattern would be, okay, so I see I have x's in all of the numerators. So this would be x to the, looks like I'm doubling, so 2n, okay? Or I'm jumping up by evens. That's another way to look at it. All the signs are positive, so I don't need a -1. The bottom matches the exponent, which is 2n factorial. Okay, so this is the sum. Another way to write e to the x plus e to the negative x over 2 is the sum from n is equal to 0 to infinity of x squared, x to the 2n over 2n factorial. All right, next, find the first 6 non-zero terms of the Maclaurin series of e to the x plus cosine x. And then we're going to use that polynomial to make an approximation of e to basically f prime of 0.5, so the derivative, okay? So first we're going to find f of x, which is e to the x plus cosine x. So I know what e to the x is. I know what cosine x is. I'm just going to write them out. So I have e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5 over 5 factorial plus x to the 6 over 6 factorial. And I'm going to do a bunch because I have the first 6 non-zero terms. So it's going to be a lot. I anticipate some things canceling. So I'm just going to write them all up. Okay. And then I'm adding on cosine x. Okay, so cosine x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial plus x to the 8 over 8 factorial. And then I'll just go ahead and add an x to the 8 over 8 factorial here. Okay, so I am going to add these up to give me e to the x plus the cosine of x is going to give me 2 plus x. These cancel, so my squared term cancels. So I have a x cubed plus 3 factorial term. The degree 4 terms, they add to give me 2x to the 4th over 4 factorial. My x to the 5th term is x to the 5th over 5 factorial. These cancel. So then I have another term of x to the 7 over 7 factorial. And let's add those up. That's 1, 2, 3, 4, 5, 6 non-zero terms. Woo! Okay. And then we'll just put our plus ... so that it goes on to infinity. Now we need to find the derivative, because what we're going to do is evaluate f prime of 0.5. Okay, so I'm going to take the derivative. Remember, this is equal to f of x. So I can take f prime of x would equal 2 becomes 0. The derivative of x is 1. We like this because it's just like a derivative of a polynomial. Okay, so x cubed over 3 factorial is just 3 over 3 factorial. Remember, 3 factorial is just like a constant, 6, okay, times x to the 4th plus 2 times 4 is 8 over 4 factorial times x to the 5th. Did I just raise those? Oh, I went the wrong way. Okay, it's not x to the 4th, it's x squared because we're taking the derivative. Okay, so this would be x cubed. I feel better. Okay, plus 5x to the 4th over 5 factorial. Okay, plus the derivative of x to the 7 over 7 factorial would be 7x to the 6 over 7 factorial plus ... So we really only have 5 terms here. That's okay, because we started with 6. And now we're going to use that to evaluate f prime of 0.5. Okay, f prime of 0.5 would be 1 plus 3 times 0.5 squared over 3 factorial plus 8 times 0.5 cubed over 4 factorial plus 5 times 0.5 to the 4th over 5 factorial plus 7 times 0.5 to the 6th over 7 factorial. Okay, I used a calculator, I can't lie. I didn't do this by hand. So we get that this value is about equal to 1.169. And we say about equal to because we didn't plug 0.5 into every single term going on to infinity. So I'm also going to put about equal sign here because we plugged into it, the 0.5 into a finite number of terms. Okay, so we think that f prime of 0.5 is about equal to 1.169. Okay, let's just get the actual value for funsies. And even though I didn't ask you to, so the actual would be f of x is equal to e to the x plus the cosine of x. You can just do this in your calculator, or this is a pretty easy derivative. So f prime of x is e to the x minus sine x, and then we evaluated f prime of 0.5. So that would be e to the 0.5 minus sine of 0.5. And I got that this is equal to 1.169 with some decimals. Look at that, matchy matchy. Okay, so our polynomial was a really good estimation of what the actual value. So this actually works. Okay, I know, feels like math magic. Okay, so we're going to use the sixth degree Maclaurin polynomial to approximate the value of the integral from 0 to 1 of sine x squared dx with a maximum, and then we want to know what the maximum error for this approximation is going to be. Okay, so I'm just going to start by saying that the sine of x expanded is going to be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus dot, dot, dot. So then we're going to plug in, because we are evaluating the sine of x squared, we're just inputting x squared in for x. So we're going to end up with x squared minus x squared cubed over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7 over 7 factorial. Okay, so we can now take the integral from 0 to 1 of sine x squared dx, which is going to equal the integral from 0 to 1 of x squared, that's the first term, minus x to the 6th over, instead of 3 factorial, I'm just going to write 6, plus x to the 10th over 120. And I think that's going to be enough. So I'm going to stop there. Okay, taking the integral. We like this because it's really easy to take the integral of a polynomial. I get x cubed over 3 minus x to the 7 over 7 times 6 is 42, plus x to the 11 over 120 times 11 is 1320. And we're evaluating this polynomial from 0 to 1. All right, so I am going to plug in, it says that I want to use I wanted to use the 6th degree Maclaurin polynomial. So when I look at my integral, I'm really using these two values. The reason why I included the x to the 10th value is because that's the first neglected term, or the first unused term, that is going to tell me what my maximum error is going to be. So I have to get the value of that so I can figure out what my maximum error is going to be. Okay, so when I evaluate this, I'm going to plug in the 1 in for x. I get 1 over 3 minus 1 over 42 plus 1 over 1320 minus, then I plug in the 0, so I'm just subtracting out 0. So I really am using only these first two terms to evaluate the integral. And then this third term is going to be the value of my error. So to estimate, I'm just going to add up. I'm going to cross this guy off. I'm going to add up 1/3 minus 1 over 42, which gives me 1/3 minus 1 over, I don't know, let's see, over 3 minus 1 over 42 gives me 0. And it's an estimation because we didn't add all the terms. So 0.309, or rounded, it would give me 0.310. Okay, so I'm adding these two only. Now the third term tells us that the maximum error is the first unused term, which has a value which is equal to 1 over 1320. So 1 over 1320 is a decimal of like 0.00075. 57 repeating, or 75 repeating. So that's the most we're going to be off for this series, or this integral, okay, using these first two terms to evaluate. Okay, that's it.